Okay, so let's get going. So thank you for the invitation to come here and give a talk in your quantum group, right? What's it called again? Quantum Collective. Quantum Collective, thank you. And then we're excited to join tomorrow, the STEM Girls STEM Day. And today I want to talk about TKET. So TKET is an advanced quantum SDK for NISQ era. And in case you want to connect with me, here's the LinkedIn, my LinkedIn information. And I want to say that I'm a quantum evangelist. So my role is to, visit universities and go out and talk about Quantinuum's kind of like software and hardware and middleware. Okay, so the first thing I want to talk about today is introduction to Quantinuum. We had a big announcement yesterday. Talk about quantum compilers, TKET components and functionalities, TKET features, performance of TKET, and some summary resources. And please just stop and ask me questions if you have some. So Quantinuum is the largest quantum computing company. So if you think about IBM and like Amazon, Bracket, or Google, they're all housed within the companies, right? But we actually are a separate quantum company, a full stack company. We have about 500 employees now, mostly scientists, over 250, and we have multiple offices all over the US. Our main office is in Bloomfield. That's where our headquarters are. It's also where it's one of our quantum computers, two of our quantum computers soon will sit. Then also we are always looking for talent. So, for example, for summer internships, you can use this QR code, check out our website. Please always, when you look for job opportunities, check out what we have open, and please apply if you see a fit. Typically, internships, they're open in November, December. So for this year, most of the stuff is closed, but sometimes you actually can still find an opening. So check that regularly, please. So Quantinuum full stack, and I'm going to try to move this if I can. Okay, so Quantinuum is a full stack quantum computer, quantum computer company, I should say. So we have our algorithms on the top, TKET is our middleware. We are going to have a quantum operating system, and then we are either accessing our H series, or we're going to access other quantum computers. So we are platform inclusive, which means more or less that we can use like CIRC, for example, or TKET or PennyLane. You can use the way I would use the algorithm there, and then you actually can use TKET to compile, and then you could again use your IBM backend or your Google backend for our hardware. Okay, so it's kind of like a middleware, but we want to make it inclusive, and the reason for it is because when we merged as a quantum company, Cambridge Quantum Computing was initially kind of developed, or it was, but Cambridge Quantum Computing was more or less a company that was formed because of making a middleware that is platform inclusive. So it was the whole idea about TKET. So this is why TKET remains to be platform inclusive. Next slide. Yeah, so pretty much Quantinuum regarding the hardware side, we always want to add qubits, but if you do that, we want to improve fidelity, increase quantum volume, and doing more with every qubits. So our backend is a trapped ion quantum computer, and we have been trying to improve our quantum computer now significantly. So over since 2020, we have improved the quantum volume by a factor of 10 every year. So just yesterday, we made an announcement of 32,000 quantum volume, 32,000. So this is industry leading. There's no other hardware that has that quantum volume. So in any case, if you're interested about quantum volume, how you calculate it, and the data, again, here's the QR code, and you can look for that yourself. But you can see that we are on a very nice trajectory. So we're keeping on our roadmap. Okay, so now let's talk about our quantum compiler, which is TKET. Let's go. Okay, so as you know, we have a quantum algorithm. You want to then convert it into quantum circuit, and then you have to run it on a quantum computer. So to do that, we use quantum compilers or quantum SDKs. So in this case here, for example, imagine you are a quantum information scientist, right? You're an end user, and you want to use gate-level quantum computers to solve your problem. You want to program in your favorite language, right? In your case, it's PyTKET, right? Which is okay. You want to run your algorithm most efficiently, and you want to get the most accurate results. And you want to make sure that you can go between the different backends easily. So obviously you have NISQ error. So we have 50 to 100 qubits we're dealing with right now. Not yet in fault tolerance, not enough to achieve the quantum advantage we're looking for yet. And it's all noise, right? So you deal a lot with noise. You have the gate fidelities. You have to deal with coherent and finite coherence times, right? Your qubit is dying more or less before you may be done with the calculation. You're adding up errors, 2 qubit gates, single qubit gates, readout errors, measurement errors, right? And then there are a lot of errors you don't know well, which is not well understood, and we are trying to figure that out. So that's what the noisy part is all about. Then, if you think about inclusive software, quantum SDK, what you need to also be aware of is different architecture, right? So you have here the Google one, IBM, and then Rigetti. And you can see that all of them have different architecture. Qubits are connected differently. Here for IBM, you have the different colors of qubit. You know what that means? Very different colors. Remember that? It's strength like the connectivity between the qubits. The connectivity is here, right? Yeah. That's this. But I believe depending on what we do click on it, on the IBM Q one, it tells us something about the error. Or coherence times, right? So there are all of these qubits have different errors, have a different coherence time, and so on. So there's actually a lot of information in this graph. So when you're trying to place your circuit onto this graph, you want to also be a noise aware placement, right? Or coherence time aware placement. So your SDK should be able to do that. And these numbers are actually updated regularly because IBM is calibrating the machines regularly.
So are those gates at the bottom? Are those like all the universal gates that you can use on each of these?
Exactly. Yes, perfect. Yes, sir. So each of these architectures have different universal gate sets. So you have to take your quantum algorithm and you have to convert it to that gate set, right? So your compiler or your quantum SDK has to do that too. You don't want to think about that. You just want to set it up, right? But if you, for example, work with error correction, for example, then you may want to actually work with that by hand. So you don't want something automatic. You actually want to understand how this works. And then here is Rigetti one, right? So similarly, so pretty much TKET was totally developed with this in mind, right? To help people to access gate level quantum computers and to solve the problems. And it was developed with this in mind, that it can handle many of the intricacies of the NISQ technology, independent of the language you're using, independent of the quantum computer you're using, and then it frees the user to focus on techniques and projects they are working on, right? So the quantum algorithms. So let's talk about the TKET components and functionalities. So, so you may have heard about TKET and then pyTKET. Have you heard about these two different? Yes. Yeah. Yes. So what is TKET? What is pyTKET? So TKET is the C++ core. This is where everything is written. And C++ is used. Do you know why we use C++?
C++ is like lower level, so it runs faster.
Exactly. Yeah. So that was the idea. So this is why TKET is written in C++ to run faster, with the trade-off that not many people can code in C++, right? So to make it universally accessible, then there's a Python with it, right? With pyTKET. And then we have extensions. So pyTKET is what we are talking to. That's what you would download if you want to work with TKET. It talks to the C++ core, And then you have the different extensions. So you have device and simulators, you have pure simulators, and you have pure transpilers. Do you know the difference between them?
Not inherently. Yeah.
Huh? So I will go into that a little bit. So device and simulators is, for example, IBM QSPIC, right? You have the device, the hardware, but they also have the emulators, right? They have the error. For example, the simulator, the emulator, right, which is hardware knowledgeable. The same with AWS, right? Azure too. And the devices, they, for example, Azure, they have multiple devices you can access, right? Same thing with AWS with multiple devices. So you can have pyTKET has these calls, pyTKET IMQ, A50, TKET, and so on, where you actually call different backends with the simulators. pyTKET TKET is the most developed quantum, kind of like the extension we have. Then simulators, these are pure simulators. And depending on which, some of these are very useful for different types of algorithms, right? And different projects. So these are pure simulators. And then you also have transpilers. For example, pyTKET PennyLane is where you take the PennyLane language, which is what?
That's my thing.
Like Xanadu, yeah, right? So you take PennyLane, right? You can use Xanadu their Quantum SDK, which is very good for, you know what is optimization and machine learning, right? And then you could use pyTKET PennyLane to like compile, optimize your circuit for a different backend, right?
So what the difference is for simulators, those are kind of like Python subpackages, whereas transpilers are for particular languages that are already, or quantum SDKs such as TKET. Sorry.
Yeah, so it's really transpiled within language, and that's it, right? Here you actually have a simulator, so you have something that can simulate your algorithm, right? So yes, so there are different things because sometimes compiler, transpiler, there are different ways. But this it's just physics. That's the ZX calculus package, right? So you can actually work in ZX calculus, and then once you have your circuit, then you can use pyTKET to compile and run again. That's the idea.
With the simulators, is it like how it would run like on an ideal quantum computer, or does it always like emulate like the behavior, like the current state of like the backends too?
It depends what you use, right? So you can have an ideal simulator, like the error, for example, simulator in TKET, or you could have the IBM Credo emulator, which has the noise model for that backend, right? Or you could have the Quantinuum H1 emulator, which is a noise model. So you can pick and choose, right? You can have ideal ones, or you can have the ones with the noise model. And TKET allows you to build your own noise model if you want to. So you could make your own backends. So you could be like, what if I could make a backend that has a Hadamard gate in the basic data set? That's something, for example, I haven't seen, right? There's no backend right now that has a Hadamard gate, right? So you could actually play around with, if I would develop a quantum computer, you could make your own backend, which is pretty cool. So very confidently, I say that there's no other quantum SDK has as many extensions TKET, and it's because it was developed always. It was initially started in 2014, so it's now 8 years that TKET has been developed, and we have been adding extensions. The way you install TKET is with pip install pyTKET, because pyTKET again is now Python wrapper, and then you do pip install pyTKET TKET, pip install pyTKET PennyLane. So this is always the same, right? So pyTKET, and then you just drop in the other quantum SDK name, what we have. So TKET is open source, and hence anyone can contribute. But I already said C++ is typically harder to do. So we have less contributions than, for example, TKET, because TKET right now is in Python. So people, it's easier to contribute. So some TKET features. This is how you write the circuit class. So very similar to TKET, you can see here. Import circuit, render computer, it's just to make a nice picture. But what I really like about TKET is that you can just keep adding the gates. So you don't have to like write line or a loop. So that's actually a really nice feature. Then this is the download button. You can actually download this as a really nice JPEG. And when you click on this button here, the first one, you actually can go between traditional and status calculus. So it's actually really nice. So if you want to know how your circuit looks in status calculus, you can actually just toggle there, which is really nice. If you're coding TKET, we have a function called TKET to TK, so to TKET or TKET to TKET, right? So you can go, it's bidirectional, and the same thing with circ, the same as bracket, you can go between both ways. This is your TKET circuit, right? So TKET circ, and then all you do is you import from the extensions TKET to TKET, you import your TKET circ, and then you have it. Okay, so it's very straightforward. So it's really this in mind that we're trying to make it very useful. This is just more code. I just want to show you that you can also call with the pyTKET extension TKET. So you do pip install pyTKET, you can do the airstate backend, right? And then you can use that. But again, you could use the airstate backend with TKET as well. And then also you have the notice simulated here if you wanted to. So I just want to show you that this is like, very similar to the quantum SDK you are used to if you use TKET. But now it comes to functionality of TKET. So circuit compilation is the main functionality of TKET. So as you know, you want to lower from a high level specification. So when you write an algorithm, it's a very high level, right? To the low level, the quantum computer understands, right? And there's a big gap. You have to retarget different hardware, right? Different gate sets, different architecture. And then you have to do optimization. You want to make the circuit smaller, smaller, and smaller. So when you run a circuit, is there something you consider before you even go run it on the backend?
Well, that's like the complexity of the circuit. It's like how.
Right, which specific gates are you looking at?
You'll be looking at like totally gates, larger gates,
Right.
gates that operate across multiple qubits.
Right, so totally gates you typically can't like implement on the hardware, right? So which gates can you
You could have meant CNOT gates.
see on this, right? And they are more expensive, right? So have you ever thought about how you can calculate if your algorithm is even worth running on a backend? No?
Not in the hardware sense, in like a theory sense, maybe, but not in hardware.
I've heard about qubit fidelity. Right. So like you have seen like 2 qubit gates, right? 0.9993%. Right. So, right. So, for example, you have this for your first device, you have this for your second device, it's 0.9997. You may not think it's a big difference, right? But when you have n 2 qubit gates, you take this number to the n. So if you take this number to the n, you can try it out. You will see that after like 100 or so, 2 qubit gates, we were like 60% error or something, right? So you really, this is a quick back of the envelope calculation you can do for your circuit. It even makes sense to run on a back, right? You look at it's a very rough estimate because you have also readout error, right, and other errors, but it gives you very good ballpark within 10%, I would say. So you maybe know the IBM Quantinuum, right? You probably use that. That's pretty accessible to you. If you want to rebase your circuit, right, to the IBM Quantinuum gate set, all you do is you import the auto rebase, you specify the gates you have or the gates your backend has, and then you just apply the rebase to the back. That's it. You rebased all the gates in your circuit. The same thing with placement. If you want to place it onto these qubits, right? If you have like you're swapping and everything you want, the same thing idea. You have a placement pass, you import the graphical, the architecture for the backend, and then again you define your backend information, the architecture, and then it just applies your placement pass. And then you place it. Okay, and you can make this noise aware. which is really nice. Remove redundancies, that's something you should know too, right? When you make a quantum algorithm, for example, it could be that quantum algorithm you generated with the functions, right? If you have your tools, you have two gates that are similar, you have to minimize them, right? If you have two right rotations, you only want to do one instead of two, because each of the time you apply a gate, you are doing error. Same thing here. So TKET has like very many passes. Each of these passes try to optimize the circuit in a way by some knowledge we have, right? So if you look at redundancies, you are again using a pass from TKET, remove redundancies, and then it should apply to your circuit.
So for example, where you see the two RYs down there, this redundancies will combine.
Right. Here it is. So it's one pass, two lines of code, right? So again, remember, you can use a TKET, everything all through a TKET. You call TKET to optimize, and then you can run it, right? So you can see, this is combined right now. This is combined, right? Here is interesting. For example, here you have an RC gate, right? NTN, but you measure in the C basis. So it's a rotation that's unnecessary. So it also falls away right there, right? It's not here anymore. So it's very powerful.
Are the measures implemented at the end of the computers automatically?
Yeah, so it's they are implemented when you do the so you have to do what I don't show here right now. For this one, yes, you're right. So I would have to do here circuit dot measure all. It's actually missing the catch correct. Yeah. So I have to do measure all. So there's a lot of compiler passes, and each of them do something with phase scatter, that's select terms. You have better replacement, resynthesis, mapping, right? You have symbolic expressions. So why would you want to use symbolic? So symbolic circuit. Have you worked with that yet? No. No. So just imagine like a function, right? You have a function f of x. And x variable is just you plot it, right? It's straight line. But x can take different values, right? So instead of writing a circuit for each of these x values, what you can do is you have symbolic circuits. So then you can optimize it in a symbolic way to minimize a function, right? Or maximize something. You don't have to always put in the values. So you optimize it overall for the symbolic ones instead of like optimizing each of these circuits.
Oh, okay.
So this is kind of like to help you with the workflow. It's not always like ideal, right? Sometimes it could be that you have a circuit that actually optimizes better if you do it individually, but it could most of the time on average it helps quite a bit for the applications for certain applications. But all I want to say is we have a lot of passes, and I think sometimes we don't know all about the passes, and these passes were specifically made for advanced users, right? So for users that have algorithm in mind, they're really working on the algorithm and then want to specifically optimize their circuit. So all I can say is if you use TKET, right, for your project, and you want to know if you use the right passes or you can do better, just reach out to us, right? So we are actually very good at getting back to our users, and we help you trying to get the right pass and sequence to get the most out of your circuit. If you don't want to play with all these different passes, which are many of, right? Just like TKET, we have our different optimization levels, which get compiled circuit. We import the circuit, level 0, level 1, and level 2, which is the default level, which is the most optimizes the most. Level 0 is just you route without optimizing. Why would you want to use level 0 without any optimization?
If it's simple 2-gate circuit, maybe.
Yeah, simple 2 gates, for example. You just maybe just want to put in the device, or for example, if you want to learn about noise, right? How noise accumulates. Maybe you want to have a lot of like certain gates after each other, and if I compile it, I would make it smaller, right? So I would make it less connected.
Yeah.
Oh, that was like 6.
Well, it's a 5. So that's okay. Sorry, everybody.
Hello.
It's being recorded.
Oh.
Yeah. So this is a circuit you may have seen before. This is the ground, energy level. You can calculate the ground state energy level from this circuit for H2 atom. And I want to show you, it's just a very old circuit. I think it's 150 or some gates. It's 56, 2 cubic gates, right? So now we want to run this circuit on the IBM device, IBM Credo, with the default paths. Without the default paths, just like routing it and rebasing it, and then with optimization. And to just give you an idea of like how powerful TKET is. If you want to know specifically which paths we have for the different optimization levels, you can look on online. We have a list for this for IBM, so you actually know all of these paths that are applied and how they are applied. So here are just some results for IBM Pure Credo. I just want to show you here. So if the circuit I just showed you had 150 gates and 56 CMOS gates. If I just route and place, right, the circuit, I'm increasing the number of gates, 250 and 115 CMOS gates. And do you know why you increase them? You just route and place from the initial circuit. Why is this gates? Why is it more? If I take the circuit, and then I put it onto this backend. And here it is. What kind of gate pops out here a lot?
Or the
Control access, right? Control access actually, that's actually a gate that's actually a fundamental gate for IBM too. But what is another gate that pops out a lot? Dagger, yeah. Hadamas, right? H gates, right? And H gates all have to be rewritten in this gate set.
Yeah.
So you're adding gates, right? So actually taking your circuit and just putting it on the architecture on using the gate set of the backend, you made it automatically worse. Like it's worse. You can't. If you take 115 to the 0.9993, it's impossible. Like you don't get any good results, right? So now, if you use TKET with the optimization level 2, you're getting 278 gates and 19 CMOS gates, and now you actually can run it. The difference here is just emulator and actually backend. So we actually ran this just to show you the difference. So here, this is before optimization. And this is after optimization. This is the correct answer, 1010 for that specific circuit I showed you when you run it through a simulator. And 42 times you get the right answer before optimization. That might not be good enough. After optimization, you get 74 times out of 100, right? So 74%. So it really increased it a lot. You also notice a lot less gates, right? So this is I say like, if you have an IBM TKET account and you use everything in IBM TKET, if you have to add like 5 to 10 lines of code to your current code base, you actually use the TKET compiler runner in the backend, and you're good to go. So all I want to tell you is TKET is so universally and so nicely set up that you should just add it in your workflow. Sometimes it will help, sometimes, depending on what you're doing, it may not optimize, but on average, it's actually optimizing better. I think there's only very, very few cases where IBM TKET is close to the TKET performance, but typically TKET outperforms IBM TKET. So it's nice enough to just add to your workflow and to make sure you optimize it the most efficiently. So now what I haven't talked about is like, if you want to go from this is how you call the IBM emulator, IBM backend. Very similar to what you see in TKET, right? you can then just import, for example, if you do the pyTKET Quantinuum extension, you can import Quantinuum backend and then you can run it on the Quantinuum backend. So again, it's only a few lines of code to switch between backends. So IBM superconducting devices still have the 2-qubit fidelity of this 0.993, and the trapped ions are more like 0.997, right? So just to show you for an emulator, I didn't run that on the back end, but just to show you an emulator, if you run it on the IBM, on the Quantinuum device, the H1 emulator, you get 92% out of 100. Okay, so the backend has a way less error, so your results are, cleaner for this specific example. Quantum chemistry circuits run very well on our backend. So in any case, this is the comparison. So you can see that before and after really is a difference, right? Applying it using a TKET compiler. So we talk about the TKET performance. So what's the history of TKET? TKET was developed in 2014, and then it was closed source, right? Till 2021. And in 2021, we made it open source. And so it's fairly new compiler in that sense, but more and more people are now using it together with IBM NISQ for benchmarking and for comparison. And it's now considered one of the state-of-the-art compilers, which is great, which we're very proud of. Sometimes you see TKET written this way, TKET. So we actually got away from this because it's difficult to search in the engine. So we now use TKET, all capitalized, in case you've seen that before. This is just a benchmark. There's a lot of different benchmarks out there. This is for quantum chemistry circuits. Arlene paper is the one. But what you want to see, the further out you are, the better you're doing. Okay. So in this case, you have physics, right? Does compare the best, then you have pyTKET chemistry passes, the second, pyTKET, and then you have like circ and NISQ in the middle, right? So you can see for this specific case, physics was the best, right? Then you maybe go to the characterized quantum dynamics, a different quantum gate set. In this case now, pyTKET chemistry was really good, right? So all I want to say here is that yes, different quantum SDKs can perform, differently, give a different outcome depending on your circuit. So that's why, Michelle, I know that you said that there's so many quantum SDKs out there, right? And you're using what you're using, but all we're saying, it's almost like you have to test them all out to make sure that you get the best if you're really trying to work out the best result on the back end, right? TKET is a good start. TKET on average is actually very good, but again, there are quantum SDKs that work really well for their specific application. This is something which I'm gonna bring now within the ZX calculus, which is nice. So the quantum chemistry circuits, these have something, the structure here, these are called phase gadgets, and these are called Clifford conjugation. And it turns out, if you go into ZX calculus, these phase gadgets can be very nicely rewritten in ZX calculus, very like compact, right? And then you would have to bring it back out of ZX calculus. But in any case, for ZX calculus, it's very powerful for optimization. And TKET is based on ZX calculus. Some of the TKET passes are. And these are the papers by Bob Cook and Russ Duncan, and then also John van der Wettering about ZX calculus, in case you want to read up more. But just want to show you now, that's the Clifford sync pass. It's the pass in TKET that has these value groups of these phase gadgets, right? These and tries to complement it. So with one single pass, I went from 56 CNOT gates to 18. Because it recognizes the structure of the phase gadgets. And this is what TKET is built on. Over the years, scientists came up with a way of optimizing specific pieces of a circuit, right? They realized, oh, this looks like that, I can represent it this way. And people have come up with algorithms doing it. And TKET, over the years, we have developed our own, like this, but we also have taken in passes from other people. So it's a collection of passes from the whole kind of like, from the entire community. And that's what we're offering, right? We offer that to the users. And so it's a very powerful tool. So yeah, one pass. So, but you have to know that. And Clifford Sim pass is actually not a default pass. So if you go back into this long list, which is really far up, I apologize. Oh, we get there. Right there. See? Actually, there is. Sorry, I'm taking it back. Clifford simplicity for the idea. But here, you notice this here? Allows swaps as false. So you actually sometimes have, for your passes, you have to be specific that your swap gates are false, because you have some backends like the Quantinuum backend, which is fully connected, right? So every qubit talks to everyone. And if you use the IBM backend, you actually have to put it in false, so it doesn't do the swapping, right? Okay. So it's a very powerful. So going back here, when you look at these papers, the pyTKET pass in this case didn't have the different sim in it for this specific paper. So that's why the chemistry pass outperforms the pyTKET pass, the pyTKET chemistry pass. Okay, so this is it. That's a Quantum Fictions book, if you haven't seen it. It's kind of like super, I'm reading through it right now, and it's pretty amazing because it's quantum computing without math. So hold on, I'm trying to get my talking thing there away. So oopsie. So can you get it? So this is you can get it on Amazon, but there's also no papers. It's built on papers, and so you can also get the papers. But it's a super cool book, and actually, you've seen it, right? I did. But it's like rules, like pictures have rules, and there's no math used to it, and so like so it's pretty neat. Yeah, so this is different resources, the GitHub user manual Slack. We get asked a lot by research groups, how can we get access to our H1 backend? Because it's the leading backend at the moment. You actually can. So have you heard about Oak Ridge National Lab?
Yeah.
Yeah. So they have you can actually get Quantinuum backend access through Oak Ridge National Lab. So you go there, you apply, so your PI has to apply for you, right, with your project in mind, and then they give you credits. And it's free. So if you want to run on the Quantinuum backend. Yeah, so the end of a message is use TKET. It's a few lines of code you can add. It helps you optimize it. You can't lose it. You only win if you use it. State-of-the-art compilation, rechargeable, works with other libraries, application-specific tools, and use other software is built on TKET. For example, we have our chemistry platform, which is in Quantum, which is built on top of TKET. And then tomorrow, if you come visit the STEM day, the girls' day, STEM day, right? We have the pyTKET bricks, the Lego bricks to play with. So yeah, thank you, and taking questions.
So as we are a quantum computing student club, we are wondering about internships. Are there any requirements, like you already had to complete your undergrad degree, or do you currently take undergrads and internships?
Oh yes, so we do actually. So depending on what role we have in mind for over the summer. We have undergrads, we have grad students, but we also teach PhD. So we actually say someone has to be a PhD program, or someone has to have has to just start graduate program, or someone is with a bachelor is fine. So depending on the role. So yes, we do that.
Okay.
So it's just kind of like keeping an eye on. It really depends on the different groups, what kind of like what they're working on right now, what they need help on. So it's kind of like a fluid thing. I can't tell you how many of each there are. I do know historically we have offered all of them.
Okay, fantastic.
I noticed earlier, like on the quantum volume benchmark, so that's like a industry standardized benchmark, right? And you guys actually run the verification like on the back end. So
Yes.
yeah, how does it like relate to like the fidelity of the students, like compared to like the actual number that like it's represented by the quantum volume? So it's like 32,000.
Yes. So you actually, if you're really interested in all the pieces that go in.
Yeah, also how is that?
Yeah, so quantum volume, I don't know exactly how it's going what's the exact equation, but what you take is you take the number of qubits and the fidelity, right? So kind of like one qubit fidelity, and you calculate that result. And if you go here to GitHub, you can find all of these things. So where's I stop sharing right now? There's actually a plot, but I can't show it right now. But if you go to this link, there's a plot that actually shows the fidelity over time, and then there's like a benchmark for the line, like 60-some%, 63, 67, 68%, and it drops below that line. Then you increase the quantum volume until it drops below, and then you say once it drops below, then it's not a test, it's no good anymore, right? So it's kind of like you have I forgot 68%, don't quote me on that, but it's you calculate a specific value of fidelity, right? Kind of like with these numbers, right? You have a quantum circuit that you're testing deeper and deeper and deeper and deeper and deeper till the fidelity is dropped off. And that quantum circuit is related to quantum volume.
I see. So it's in the circuit.
Yeah.
Okay.
And obviously, the deeper you go, the longer coherent times you need, right? The deeper you go, the more 2 qubit gates you have, and so on, right? So it's a specific test, and the quantum circuit is defined. You know, there's the quantum volume was initially developed by IBM, right? So there's like an algorithm for that, and then now it has been implemented. But because we are starting to. People are now in industry actually talking about some different value, because it's getting really weird to say like 100,000, 1 million, right? So it's like here, more like between 1,500. I felt like it was more, you could comprehend a little bit more, right? But the quantum volume as a number just growing so fast that it becomes a really large number. So I don't know what the industry or like the community will do regarding the benchmark. Yeah.
Can you go back to the slide regarding each of the architectures of each of the computers?
Yes. Which was, I think at the beginning, right here.
So those three are for Google, IBM, and TKET. So are each of these constituting like a different lattice structure for each quantum computer, I guess?
Yes. So I'm assuming here this is a qubit, right? And then this qubit can interact with this qubit. I think this is the qubit is the X, sorry. So qubit is the X adjacent coupler. These are couplers. So this qubit can talk with this qubit, and this qubit can talk with this qubit, right?
Yeah.
So this can talk with 4 qubits, right? So yeah, it's a different chip with a different qubit connectivity. IBM, right? You actually can't see. I don't see anywhere where you have sort of Google one. Actually, you have a qubit that can interact with 1, 2, 3, 4. IBM can, IBM has 1, 2, 3, 1, 2, 3, 3 the most, right? Here you actually have 1, 2, 3 also, but only these ones are 1, 2, 3, right? These are only like linear. So yeah, so each of these chips is different. So I don't know if you there's Fleximo, which is a company. They actually build chips for your specific application. So they're trying to place the qubits the way you want them to interact.
Oh, and what that would depend on is the algorithm.
Right. Yeah. So you can make a specific chip just for your algorithm. So it gets very specific, right? But you can imagine that might help.
Yeah.
Right. And then there are other things in neutral atom computers.
Yes.
Where you can actually place the qubits too. I think the way you do.
So I don't know if you're allowed to talk about this, but do you know what Quantinuum's solution is?
We are fully connected.
Oh, okay.
So Quantinuum, we have we take rubidium atoms, we strap them up in that electron, so they're like ions, and then we put them in a potential well. So we have them on a chip, and then we move them around. So if you want to have two qubits interact, we just take these qubits and we move them together. We can actually also switch position. So they're all loaded on a linear track right now. So our H1 chip is linear, so they're all loaded in. So they sit up somewhere on the track. And then we can go pick them up. They're all in a well, right? And then we can say, oh, this one has to talk to this one. It's bringing them closer together. And if two qubits, if one qubit can't pass the other one, we rotate them. We swap them around and go there. So we actually have fully connectivity. The downside is that going from here to here and having like, so we have our 20 qubit chip, 18 qubits in between. You have to do a lot of this swapping, right? Till you find each other, right? So it's time consuming. So luckily, like trapped ion quantum computers have a very long coherence time. So actually, overall, we have a longer coherence time than the superconducting, for example, but it just takes a really long time. So if you have an algorithm, for example, where you talk a lot between the classical part talks a lot with the quantum part, and there's a loop where they go back and forth a lot. Trapped ion is really slow, right? So then we want to possibly use superconducting quantum computers.
Okay.
This goes to something where people still don't know which quantum computer is going to be that quantum computer. We believe actually there's not going to be something like that because of exactly what you said. Some of them are fully connected, have really good qubit fidelity, gate fidelity, I should say, but then it takes too long for a given algorithm to make sense to be implemented, right?
Yeah.
So we think that actually different quantum computers will have different applications eventually as we push the field. Yeah. Just like, in classical computing,